And you will see that many things are very similar, but of course we are going to learn new things as well in this section. Okay, first we know that if a generator's EMF output is a sine function. This is what we know from section 2. And EMF equation for a generator is E max sine omega t. E max sine omega t. And because according to Ohm's law, without EMF, without potential difference, there is no electric current. If there's a potential difference, there's an electric current. You know that. So that's why electric current of a generator will have exactly the same function of the induced EMF. Yeah, induced EMF is E max sine omega t. So electric current function is going to be I max sine omega t. So these values are called instantaneous values. So this E and that I are instantaneous value of induced EMF, instantaneous value of the electric current. And remember, there was a question, this exam question in your book, which of the following changes as that current is induced. So these values are changing, E as a function of sine. This I is changing as a function of their instantaneous values that they change. But for a generator, E max is constant value. Remember, VAN omega. Omega is 2 pi F. F is 15, Asia, Europe, and Africa 50, and it's constant. That's why E max is constant for a generator outside there. And I max is going to be changed depending on the outside resistance. I will talk about it later. But this is E max is constant, omega is constant, but E is changing as time goes, instantaneous value. But in this section, instead of E is equal to E max sine omega t, we are going to change it to V. What is V? Potential difference. So we know that in fact induced EMF and potential difference are defining the same thing. So only in this section we will change E to V, and our generator's potential difference equation is going to be V max sine omega t. Only difference is this: we don't use E max sine omega t. Instead, we will use V max sine omega t. And both current and EMF, from now on we will say potential difference of a generator vary as a sine function, sine graph. So maybe you remember this. This is the sinusoidal variation of the EMF of a generator. Now we will say that sinusoidal variation of potential difference. And it changes between two maximum values, positive V maximum and negative V maximum. And how can you calculate? You know from chat section 2, VAN omega. And because potential difference causes electric current, without potential difference, no electric current. So we can say that electric current equation also is going to be a sinusoidal function. So it will change again between two maximum values, between the positive I maximum and negative I maximum. This electric current of a generator will change as sinusoidal, just like the potential difference. Yani potential difference of a generator, output potential difference of a generator, and output current of a generator will change as a sine function, yani sinusoidal. They are identical or equivalent or similar, how you say that. Only instead of V we are going to write I. Instead of Vm we are going to write Im. Instead of negative Vm we will write negative Im. In this section we are going to study some AC circuits, and these AC circuits will consist of some elements, some components. These components are, one of them is AC generator. This is a symbol of an AC generator. AC generator out there as such a symbol. This sign is representing alternating current. Alternating current. Yani you are going to draw a circle and you will write an alternating current sign inside. This is the symbol of an AC generator. And resistor, you know, resistor symbol. This is the symbol of a resistor. So these zigzags are representing the opposition of a conductor to electric current. And we defined in section 5.2 45 degree about this one. Resistance is opposition of a conductor to flow of electric current, and it is represented by this. And generally we write in here how much is the resistance on the about this symbol. And two new components you are going to learn in this section. One of them is capacitor. Capacitor normally 11th grade title, but you didn't study that part. So first, when I come in this title, I am going to explain what capacitor is to you, then we will continue. This is a symbol of capacitor, a bit different than battery. Yes. Because remember, battery has one side, one leg is longer, the other one is shorter, but it's not like this. Equal length. So this is the capacitor symbol. This one is also capacitor, but this is variable. Variable capacitor. And if you put an arrow across a capacitor, it is symbol of a variable capacitor. Variable capacitor. And also we do the same thing for resistor. Remember, there was a variable resistor rheostat. For rheostat, you are going to draw it like this. Generally, we do it like this, and you put an arrow. This arrow is saying that this is variable. This device is a variable device. And coil, of course, coil. Now we will say this coil inductor. Inductor. Maybe you remember 561, we talk about the coefficient of self-induction. Yes. Self-induction, induction, inductance. Now inductor is the coil. The name of that coil is called now inductor. Sometimes it can say coil, but mostly we will use inductor for this coil. And this is the symbol of a coil, so symbol of a inductor in a circuit. And we are going to study those components in our circuits. This is resistor in a DC circuit. Now I'm going to compare, in the first title of this section we will compare DC and AC circuits. DC circuits, normally, I defined before, this circuit consists of a battery. So this is a battery with negative and positive terminal. DC battery, this represents. And this battery has an EMF of 15 volt. And this battery is attached to a resistor whose resistance is 3 ohm. Electric current in a DC circuit, electric current flows in one direction. We learned that before. It starts from positive, leaves from positive, and comes back to negative. So it circulates clockwise or counterclockwise depending on which side is positive, which side is negative. But it's one directional. Yeah, electric current flows in one direction through the resistor. For example, in here, from left to right, electric current flows. And these electrons, electric current is the motion of the electric charges, we learned this before. These moving charges collide with other atoms or other electrons which are not mobile. And collision of the moving charges with other atoms or other particles in the substrate material results in resistance. We defined this before. Resistance is as a result of the collision of electric charges, electrons which are in motion, with other particles which are not in motion. So produce a resistance, and because of this resistance, because of these collisions, of course, these mobile electrons will lose their energy. They will lose their energy. This energy will appear as a heat when they collide with other electrons. Yeah, all the heaters at your home, and electric heaters, are working on this principle. Yeah, while electrons are moving through this conductor, they collide with other particles. When they collide with other particles, they lose their electrical energy. This energy is converted to heat. Yeah, the result of these collisions is there appears to heat in a DC circuit. AC circuit is a little different than DC. In AC circuit, we are going to use an AC generator. This is the symbol of an AC generator, and we put a resistor again here, resistor of 3 ohm. But when we are writing the EMF or potential difference of AC generator, we only write its maximum value. Yeah, maximum value is constant. But V is changing as time goes, sinusoidal. V is not constant. V is changing between negative maximum and positive maximum depending on time. Maybe omega can be written as well. Omega is also constant for a DC generator. We can write it as well. We will write it. You will see that. But V and T will not be written So V will be depending on, as time goes, we changes. Then what is the maximum EMF, maximum potential difference of this generator? What is maximum potential of this generator? 15. Instead of Vm, remember V is equal to Vm sine omega t. Instead of Vm, what we wrote in here? 15. 15 volt is the maximum potential difference of this generator. And another difference of the AC circuit is, in AC circuit, electric current becomes one positive, one negative. One positive, one negative. But in DC, it is always positive. So this one positive, one negative says you that electrons are moving, if it is positive, to the right, when it becomes negative, to the left. So electric current flows back and forth through the resistor. They are not one directional. Right, positive, left, negative. Right, positive, left, negative. So electrons are vibrating in an AC circuit. They don't travel in one direction. So electric current flows back and forth through the resistor. Of course, when they are vibrating, they still collide with other atoms. Of course, because of this collision, there will be a resistance again. Resistance exists. And also, electrical energy will be given out by the AC generator as well. So, collision of the vibrating charges. The only difference in here is vibrating charges. In here we said moving charges. Because in one direction, charges are moving here, but in here charges are vibrating. But still they collide with other atoms, with other electrons. So there is still exists resistance, still exists in here heat. Because of these collisions, these charges, the electrons lose energy. Because of the collision, they lose energy. This lost energy is converted to heat. So Ohm's law holds for both AC and DC circuits. You know what Ohm's law is? Ver can be changed to this way. V is equal to I times R. So if you want to calculate electric current, what you have to do? You are going to divide both sides by R. So I is going to be V over R. So you can calculate electric current in AC DC circuit, and also you can calculate electric current in the AC circuit, both of them with the same equation. Now in here, let's calculate it. How much is potential difference? 15. How much is resistance? Divide them.
E over R?
Yeah, 5, 15 over 3, 5. In here, the resistance, electric current is 5 ampere. So electric current is 5 ampere all the time. But we know that DC never changes, DC current. Always constant number and always a positive, one direction. But in here, we cannot calculate instantaneous electric current. We can calculate only maximum value, because maximum value, the potential difference is given to you. If the max is given to you, so you can calculate only I max by same equation again. I is equal to V over R. Only you should change I to Im, V to, yeah, Im is equal to Vm divided by R. How much is Vm? 15. How much is R? 3. 15 over 3. 5 ampere is the maximum electric current of this circuit. Now what is the difference between them? In here, electric current is always 5, all the time 5. But in here, maximum value of the electric current is 5. Yeah, it's not always 5. It's changing between positive 5 and negative 5. Now I will draw the picture, and you will see that. This is how potential difference in electric current is represented in a DC circuit. Potential difference is 15 volts. Electric current is 5 ampere. This is representing potential difference of DC and electric current of DC, but AC will be different. So in AC, potential difference is changing. This red graph is representing potential difference. It's changing between positive 15 and negative 15, but electric current is changing between positive 5 and negative 5. Blue graph is representing, sorry? Who wrote this? Who did this? Who? You? Okay, between positive 5 and negative 5. This is how we represent electric current and potential difference in an AC circuit. Both AC circuit and DC circuit generate electrical energy and electric power. First, we are going to define what power is. In fact, we defined this before.
Yes, in chapter.
The rate at which electrical energy is converted to internal energy in a resistor is called power. It defines power of the resistor. Power of resistor. So this is the definition. It's a rate. When it says rate, we know that something must be divided by delta T. Absolutely, we will define something by delta T. But rate of what? Electrical energy is converted to internal energy. Internal energy is what? Internal energy is sum of potential energies and kinetic energies of the particles inside a substance. In fact, in chapter in 10th grade, you defined this. And sum of the kinetic energies and potential energies of particles inside a substance is called internal energy. Basically, internal energy is proportional to temperature. Yeah, if internal energy increases, temperature increases. If internal energy decreases, temperature decreases. This is what it tells you that. Yeah, in here, it basically tells you that when the electrical energy is converted to internal energy, what happens? Temperature of the substance increases. Now I will define how we calculate electric power. This is the resistance of the resistor R, and electric current through the resistor is I, and potential difference between the ends of the resistor is V. First, I will define it in terms of DC current, then we will apply it to the AC. So we know that without potential difference, current is not possible. So electric current only exists if there's a potential difference between the ends of the device. So as you see, there's a potential difference between the ends of the resistor. Absolutely, there will be an electric current from a point at high electric potential to a point at low electric potential. And how can we calculate electric power? Now I will do the equation. Power of a resistor is calculated by product of electric current and potential difference of the resistor. And you will multiply I through the resistor and V between the ends of the resistor. When you multiply these two, I times V, you will calculate power of that resistor. Proof. Yeah, sometimes you are learning this one. Proof. It's used as what? Before we talked about this, I think in chapter 4, and we are talking about the sound intensity. Power of the unit of power is what? Still what? It doesn't change. But we can rewrite this equation into alternative forms. One of them is, by using Ohm's law, we can insert, instead of V, its equivalent. Remember V is equal to what, huh?
Yes.
Yeah. Instead of V, I will write I times R. Yeah. I will write here I times R instead of V. So it becomes I squared times R. If we insert here I R instead of V, I times I, R squared times R. One of the equations is this. And we will use this more frequently. Yeah, this equation, I squared times R, in this section will be used more frequent than this equation. So this equation tells you that power of a resistor is proportional to square of the electric current. Yeah, if the electric current doubles, power increases by 4. This is I squared. Okay, you have to know this. If the electric current through a resistor doubles, because it is squared, power of the resistor increases by 4. But we can rewrite this equation in another form. Instead of I can write V over R. It's also possible. We can write it. Instead of if I write V over R, this equation changes to V squared over R, because V over R times V squared divided by R. This is going to be used in one other question, not as frequent as this one. Yeah, this one is the most frequent one we will use. One question we will use the equation V squared over R. And in fact, these two equations are obtained from the basic equation, only we are going to insert its equivalent according to Ohm's law. This is how we calculate power in a DC circuit. this equation is about the DC circuit. Yeah, when in the 11th grade, if you study this title, you will learn them. You will do many practices with these equations. Only DC is this, yeah.
Teacher, now P is not proportional with V squared.
It's proportional to square of V as well. Yes.
So V increases by...
Of course, as V increases, power also increases by square of that. For example, if potential difference is doubled, power of the resistor is increased by 4. It's similarly with the electric current. Two currents now we'll compare. This first cycle is comparing two electric currents, two circuits. One of them is AC circuit, the other one is DC circuit. Okay. We will give equal currents to both AC and DC. At equal maximum currents, energy produced by an AC circuit and DC circuit are not equal. Why do you so? Why do you think so? This is an AC circuit, huh? AC circuit, you know, only 5 ampere is the maximum value. Okay, negative 5. I forgot again, it's going to be negative 5. Your mass is positive?
Yes, positive.
Negative 5, positive and negative 5. Okay, this is, in here, maximum value of the current is 5 ampere. In here, always 5 ampere. So now the question, according to power is equal to I squared times R. If, say that R's are equal for both circuits, which circuit will have a greater power?
The DC.
AC or DC? Why DC?
Because continuously is 5.
Yes, it's continuously 5.
Yes.
But AC? 0 increases, maximum 5 at an instant only, then decreases again, becomes 0, increases, and this is always 5. But this is 5 at some instant, not always. For example, where it is 5, T1. When? T3. When? T5. Now when? T7. But all other points is less than 5. That's why power provided by an AC circuit always will be less than power provided by a DC circuit. How? If we keep their maximum currents, same. Yeah, 5 and 5. This is 5, that is also 5. 10 and 10, 20 or 20. We should keep them the same. And at equal maximum currents, energy produced by an AC circuit and DC circuit are not equal. At equal maximum current, power dissipated. Dissipated means given out. Given out. So we'll use this dissipated as several times. Given out. Power dissipated in a circuit is less than power dissipated by a DC circuit because current is maximum only at some instant, but in DC circuit, current is maximum at all instants. That's why a DC circuit will have greater power than an AC circuit if we keep them their maximum currents the same. Or an AC circuit will have less power than a DC circuit if we keep them their maximum currents the same. But how big or how much smaller is the power of an AC circuit than the power of a DC circuit? It is half. At equal maximum currents, power dissipated means given out. Power dissipated in a AC circuit of the maximum current IM is equal to half of the power dissipated in a DC circuit of the steady current IM. Yeah, if AC circuit will have a power less than DC, but how much greater, how much less? Half of it. Half of D. This is the statement you have to know. Okay, now let's write the equation for power dissipated in a DC circuit. What is the equation? I squared times R. We gave this equation. So this is the power in DC circuit. So how much is the current? IM. Square of IM multiplied by resistance of the resistor. IM squared times R. This is equation for calculating the power of a DC circuit. But this statement tells you that in the same maximum value, AC circuit must have a power less half of that number. Then I will divide this by 2. So let's try the equation then. Power in AC circuit is going to be Im squared I divided by 2. Why? Where does this come from? Half. So then we can say that this is an equation for calculating the power of an AC circuit. Im squared R divided by 2. This is power of a DC circuit, which is Im squared I, just Im squared times R. Okay, such a question can be given to you. For example, maximum current in an AC circuit is 10 ampere. What is the power of a resistor whose resistance is 10 ohm? Calculate it. So it's an AC circuit. So I'm going to use this equation. Power of AC is what? Im squared times R divided by 2. Okay, Im is how much? 10. Square root of 10 times R is how much? 10 divided by 2. 10 squared is 100. 100 times 10,000. 1,000 divided by 2? 500 watts. But if it the question about DC circuit, so current of a DC circuit is 10 ampere. How much is the power of 10 ohm resistor? It's going to be 1,000. Okay, then moreover, power dissipated in a DC circuit of a maximum current Im is twice the power dissipated in an AC circuit. Yani, I wrote both statement in reverse. Power of AC is half of power of DC. Power of DC is twice of power of AC. This is an exam question.